What happened to Comet Atlas on September 7th, during the lunar eclipse, is rewriting everything we thought we knew about this mysterious interstellar visitor. Just a month earlier, astronomers confirmed Atlas was producing virtually no diatomic carbon. Yet, almost without warning, it erupted into a dazzling green fluorescence, displaying molecules that prior spectroscopic studies claimed were absent. And this was only the beginning, a chain of discoveries that could upend the established physics of comets. As the world watched Atlas draw closer to perihelion, the Hubble Space Telescope captured something unprecedented, a sunward extension of scattered light, 10 times longer than the comet itself, stretching directly toward the sun. This defied the conventional rules of radiation pressure and shook astronomers' confidence in long-standing models. Meanwhile, viral claims of a massive second comet, hurtling toward Earth, only fueled confusion. In truth, that object was Comet Bernoulli-Bernstein, whose distant, slow approach had been mistakenly conflated with Atlas's spectacular and unusual activity. Before we dive deeper into this cosmic mystery, I invite you to like this video, subscribe to the channel, and drop a comment below telling me where in the world you're watching from. It's always incredible to see how people across the globe connect through these stories of discovery, from stargazers under quiet night skies to city dwellers looking up from the brightest skylines. Now, let's uncover what really makes Comet Atlas so extraordinary. This week's data dives even deeper into the enigma. Atlas's cyanide production is spiking at rates that follow a power law with an exponent of 9 mathematical behavior, indicative of chemistry unlike anything observed in comets within our solar system. TESS observations reveal that Atlas was already active in March, while still beyond Jupiter's orbit, defying our understanding of volatile sublimation thresholds. Critically, Avi Loeb's analysis of Hubble images reveals geometric corrections that make this sunward phenomenon even more extreme than initially reported, potentially forcing us to rethink our basic assumptions about how interstellar objects react to stellar radiation. Data from the upcoming Mars encounter in 2 weeks will either confirm we're witnessing exotic physics or reveal that Atlas operates under previously unknown rules. But first, we must decipher the meaning of its green transformation, a clue to chemistry, potentially exclusive to materials forged around alien stars. Before proceeding, I encourage you to like and subscribe if you enjoy these in-depth scientific explorations designed for relaxation, focus, or sleep. You can also boost this video using the new hype feature below. In the comments, tell me your location, the time, and the strangest scientific phenomenon that captivates you. I'll respond to many of them, and your ideas might inspire our next video. Now, let's return to our green glowing visitor and the global mystery it presents, the impossible green transformation. For months, every spectroscopic analysis of Atlas indicated a distinct reddish hue, consistent with expectations for ancient interstellar material. This color signature suggested primordial compounds, perhaps untouched for billions of years, as this cosmic time capsule journeyed through interstellar space. Then, on September 7th, during the lunar eclipse, something changed. Yerger and Raymond's photographs unveiled an unmistakable emerald glow emanating from Atlas. This wasn't subtle. This wasn't an artifact of processing or atmospheric effects. The shift from red to green signifies a fundamental alteration in the chemical processes within Atlas's coma, the surrounding envelope of gas and dust. Avi Loeb of Harvard, whose unconventional interstellar object theories have generated both fascination and debate, immediately recognized the significance. Typically, a comet's green coloration stems from diatomic carbon molecules, pairs of carbon atoms, fluorescing under solar radiation. However, the mystery deepens. Just a month earlier, astronomers at Kitt Peak Observatory specifically searched for carbon chain molecules, including diatomic carbon, in Atlas's spectrum. They found virtually none, a notable absence that ruled out diatomic carbon as a major component. Yet weeks later, the comet glows green, seemingly displaying the signature of those very molecules. What accounts for this dramatic shift? Several explanations arise from the limits of our current knowledge. The sun's intensifying heat might have penetrated deeper layers of the comet's nucleus, sublimating previously hidden reserves of carbon compounds. We might be witnessing the activation of chemical processes not observed in our solar systems. Comets, reactions occurring only under specific conditions present in this alien visitor. Or, as some researchers cautiously suggest, the green glow might not originate from diatomic carbon at all, but from an entirely different, yet-to-be-identified molecule. This possibility opens a window into chemistry potentially prevalent in Atlas's originating star system, yet completely alien to our cosmic neighborhood. Beyond the captivating color change, the comet's brightness behavior presents an equally significant development. As of mid-September, Atlas is exceeding all predictions, brightening far faster than any model anticipated. The Comet Observation Database, maintained by the CRNIV Observatory, clearly shows a deviation from expected behavior. Initially discovered at magnitude 17, barely visible to even the most sensitive telescopes, Atlas surged to magnitudes 12 through 14 by the end of September. Its trajectory suggests it could reach magnitude 12 by late October, potentially becoming the brightest interstellar object ever observed, though still requiring a telescope for human viewing. This rapid brightening indicates a massive surge in outgassing activity. Dr. Adina Feinstein's team at Michigan State University, analyzing pre-discovery images from NASA's Transiting Exoplanet Survey satellite, TESS, found evidence that this acceleration has been ongoing since March, when Atlas was still beyond Jupiter's orbit. The comet has been active at distances where our solar system's comets remain completely dormant. The implications extend beyond simple sublimation rates. Kwani Yi at the University of Maryland notes that Atlas's brightening pattern is more consistent with dynamically old comets from our own Oort cloud, objects that have made multiple passes through the inner solar system. Yet, this interpretation creates a paradox. How can an interstellar visitor on its first solar encounter behave like a comet with a long history of solar exposure? Perhaps the most baffling discovery emerged from a careful analysis of Hubble Space Telescope images from July 21st. Avi Loeb and Eric Mamajek's investigation revealed an unprecedented phenomenon in cometary science, an extended glow stretching not away from the sun, as traditional comet tails do, but directly towards it. This sunward extension, termed an anti-tail, appears to be 10 times longer than the comet's width after correcting for our viewing angle. No comet in recorded history has exhibited such behavior. Traditional comet tails form when solar wind and radiation pressure push material away from the nucleus. The physics of an anti-tail pointing sunward challenges our fundamental understanding of how these objects interact with stellar environments. The implications resonate across numerous fields of study. If Atlas is generating some form of directed outgassing towards the sun, the mechanism remains entirely mysterious. Solar heating should create symmetric expansion or preferential outgassing from the sun-facing hemisphere, not the focused, beam-like structure observed in Hubble's images. Some researchers have quietly begun exploring the possibility that Atlas's behavior is inconsistent with a purely natural object. The alignment of its trajectory with the ecliptic plane, the unusual chemical composition, the anomalous brightening, the color transformation, and now the anti-tail. These characteristics create a pattern that stretches the boundaries of coincidence. The Very Large Telescopes. Observations on August 25th revealed yet another layer of mystery. Both cyanide and nickel production from Atlas increased dramatically as the comet approached the sun, following a power law with an exponent of approximately 9. This represents one of the steepest production rate increases ever measured in cometary science. Even more intriguing, the nickel appears without accompanying iron, A combination occurring naturally in only a few specific contexts. Industrial nickel alloys produced through human metallurgy often exhibit this nickel without iron signature. While this doesn't necessarily imply an artificial origin, it adds another unusual characteristic to an already anomalous object. The Webb Space Telescope's analysis revealed that Atlas's coma composition is dominated by carbon dioxide, 87% by mass, with carbon monoxide comprising 9% and water accounting for most of the remaining 4%. This ratio differs significantly from both previously observed interstellar comets and typical solar system comets, suggesting formation conditions unlike anything in our immediate cosmic vicinity. The rapid increase in cyanide production as Atlas approaches the sun raises questions about the stability of organic compounds within the nucleus. Cyanide, while naturally occurring in comets, typically appears at relatively constant rates. The exponential increase observed in Atlas suggests either unusual chemistry or structural characteristics we don't yet understand. October 3rd marks a crucial milestone in Atlas's journey, its closest approach to Mars, passing within 28 million kilometers of the red planet. This provides an unprecedented opportunity for detailed observation using spacecraft designed for Martian exploration. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter will turn their instruments toward the interstellar visitor, attempting spectroscopic analysis and imaging. Despite the comet appearing as less than a single pixel in their cameras, the high-resolution stereo camera and color and stereo surface imaging system, typically focused on Martian landscapes, will instead peer into deep space, searching for clues about alien chemistry. More significantly, these observations will occur during Atlas's most active period, as solar heating drives maximum outgassing rates. The spectrometers aboard both missions may detect additional chemical signatures that Earth-based telescopes cannot resolve, potentially solving the mystery of the green transformation or revealing new complexities in the comet's composition. The timing also allows comparison with NASA's Perseverance and Curiosity rovers, both of which carry instruments capable of atmospheric analysis. While the rover's primary mission focuses on Martian geology and astrobiology, their atmospheric monitoring equipment might detect any particles or gases released by Atlas as it passes through the Martian neighborhood. November brings another observational opportunity as ESA's Jupiter Icy Moons Explorer, JUICE, currently en route to the Jovian system, attempts observations of Atlas using multiple instruments. The spacecraft's position will provide a unique vantage point for studying the comet's behavior as it begins its outward journey from perihelion. The spacecraft carries ultraviolet spectrographs, designed to analyze the chemical composition of Jupiter's moons and magnetosphere. These instruments may detect spectral lines from Atlas that are impossible to observe from Earth due to atmospheric interference, potentially revealing the source of the mysterious green glow or identifying additional chemical signatures. Coordination with NASA's Europa Clipper mission offers the possibility of simultaneous observations from multiple positions, creating a three-dimensional view of Atlas's coma structure and activity patterns. The twin ultraviolet spectrographs on both spacecraft represent the most advanced instruments available for detailed chemical analysis of the comet during its most active phase. However, technical challenges complicate these observations. JUICE currently uses its main antenna as a heat shield while passing close to the sun, limiting communication to slower data rates through backup systems. Results from any Atlas observations may not reach Earth until February 2026, months after the comet has passed perihelion and begun fading. Amid the excitement surrounding Atlas, social media and certain news outlets have begun circulating claims about a second, even more massive comet entering our solar system. This narrative seems to stem from confusion between Atlas and Comet Bernardinelli-Bernstein, C/2014 UN 271. Comet Bernardinelli-Bernstein is indeed enormous, with a nucleus diameter of approximately 140 kilometers, making it roughly 100 times larger than typical comets. However, this giant is not a new arrival or a second interstellar visitor. Discovered in 2021 through analysis of archived images dating back to 2014, Bernardinelli Bernstein has been slowly approaching our inner solar system for years. The confusion intensifies because Bernardinelli Bernstein will reach its closest approach to the Sun in January 2031, more than 5 years away. At its nearest point, it will remain beyond Saturn's orbit, never entering the inner solar system where Earth and Mars orbit. While genuinely massive and scientifically fascinating, it poses no threat and won't become visible to amateur astronomers. Recent observations have detected carbon monoxide jets erupting from Bernardinelli Bernstein's nucleus, confirming its cometary nature and indicating increasing activity as solar heating penetrates its massive bulk. The Atacama Large Millimeter/Submillimeter Array, ALMA, has mapped these jets, revealing asymmetric outgassing that suggests complex nuclear structure and rotation. The hype surrounding a second massive comet appears to result from a misunderstanding of the timeline and nature of Bernardinelli Bernstein's approach. Social media algorithms optimized for engagement rather than accuracy have amplified these misconceptions, creating viral content that conflates multiple distinct astronomical objects and events. Recent analysis by Zabia Perez-Cuto's team at the University of A Coruña has traced Atlas's path backward through 10 million years of galactic motion, attempting to identify its origin star system. The results are both fascinating and frustrating. No single star system shows clear evidence of ejecting Atlas within the time frame suggested by its trajectory. This absence of an obvious parent system raises questions about the comet's true age and origin. If Atlas spent significantly longer than 10 million years wandering interstellar space, its point of origin becomes increasingly difficult to determine. Gravitational interactions with multiple star systems could have altered its trajectory numerous times, obscuring its original path. Alternatively, Atlas might originate from the galaxy's thick disk, a population of older stars distinct from the thin disk, where our Sun resides. Dr. James Davenport notes that the comet's galactic trajectory aligns with thick disk kinematics, suggesting formation around ancient, metal-poor stars that existed when our galaxy was young. This possibility makes Atlas not just an interstellar visitor, but potentially a relic from cosmic dawn, carrying chemical signatures from stellar environments that no longer exist. The unusual composition, including the dominance of carbon dioxide over water, might reflect formation conditions around stars with different metallicity than our Sun's neighborhood. Dr. Feinstein's analysis of TESS images revealed Atlas in photographs taken during May 2025, 2 months before its official discovery. These pre-discovery observations show the comet already displaying significant activity at distances where solar system comets remain completely dormant. The TESS images required sophisticated processing to extract the faint comet signal from background stars and instrumental noise. By combining multiple exposures and filtering starlight, Feinstein's team revealed a fuzzy object showing clear signs of coma development. This confirms that Atlas began outgassing at approximately 6 astronomical units from the Sun, twice the distance where Jupiter orbits. Such early activity suggests either unusual volatile composition or structural characteristics that make Atlas more sensitive to solar heating than typical comets. The Zwicky Transit Facility data extends observations back to March, when the comet was beyond Jupiter's orbit but already showing detectable brightness variations consistent with active outgassing. This extended activity timeline provides crucial data for understanding Atlas's behavior as it approaches perihelion. The brightening rate follows a power law with an exponent of -3.8, significantly steeper than the interstellar comet Borisov, but consistent with dynamically old comets from our own solar system. The September transformation to green emission presents one of the most intriguing mysteries in modern cometary science. Several mechanisms could potentially explain this sudden appearance of what appears to be diatomic carbon fluorescence, each with different implications for our understanding of Atlas's nature. Solar heating might have penetrated through surface layers that previously shielded subsurface carbon compounds from sublimation. As Atlas approaches perihelion, increasing temperatures could reach deeper into the nucleus, accessing reservoirs of carbon-rich material that remained frozen during the comet's interstellar journey. Alternatively, the green glow might result from chemical reactions between previously separated compounds, now brought together by the disruption of the nuclear structure. Solar heating doesn't just sublimate ices. It can fracture the porous structure of cometary nuclei, create new pathways for volatile transport, and facilitate mixing. A third possibility involved molecules other than diatomic carbon producing green fluorescence under specific excitation conditions. While diatomic carbon is the most common source of green cometary emission, other compounds can produce similar spectral signatures under particular circumstances. The unusual chemistry of Atlas might involve fluorescent molecules not typically found in solar system comets. The timing of the transformation, coinciding with increased solar heating as Atlas approaches perihelion, supports thermal activation of previously dormant chemical processes. However, the suddenness of the change suggests a threshold effect rather than gradual activation, implying complex chemistry or structural changes within the nucleus. Recent polarimetric observations have revealed another unusual characteristic of Atlas, an extremely deep negative polarization of -2.77% with a low inversion angle of 6.41 degrees. These values place Atlas outside the normal range for both solar system comets and the previously observed interstellar comets. Polarization measurements reveal information about the size, shape, and composition of dust particles in the coma. The unusual polarization signature suggests that Atlas ejects dust with characteristics significantly different from typical cometary material. This could indicate unusual composition, different formation conditions, or structural modifications during its interstellar journey. The negative polarization at small phase angles combined with the low inversion angle suggests dust grains with high albedo and unusual optical properties. Such characteristics might result from coating with organic compounds, crystalline structures formed during slow cooling in interstellar space, or a composition dominated by materials rare in our solar system. These polarimetric measurements provide independent confirmation that Atlas differs fundamentally from both solar system comets and the other known interstellar visitors. The combination of unusual chemistry, anomalous brightness behavior, mysterious green transformation, and distinctive polarization creates a profile unlike any previously studied object. Hubble Space Telescope observations have progressively refined estimates of Atlas's nuclear size, with recent analysis suggesting a diameter between 440 meters and 5.6 kilometers. This range spans nearly an order of magnitude, reflecting the difficulty of separating nuclear brightness from surrounding coma emission. The uncertainty in nuclear size directly affects calculations of mass, density, and composition. A smaller nucleus would require higher activity rates to produce the observed coma brightness, suggesting either unusual volatile composition or structural characteristics that enhance outgassing efficiency. A larger nucleus could harbor greater reserves of exotic ices while maintaining normal activity rates. Spectroscopic analysis indicates that the nucleus itself might be unusually dark, reflecting only a small fraction of incident sunlight. This low albedo could result from organic compounds formed during irradiation in interstellar space, carbon-rich composition reflecting formation conditions around different types of stars, or surface modifications during the comet's long journey between star systems. The combination of uncertain size and low reflectivity complicates efforts to understand Atlas's internal structure and composition. Advanced thermal modeling incorporating data from multiple wavelengths and observation geometries may eventually resolve these ambiguities as the comet approaches maximum activity near perihelion. ATLAS displays an activity profile unlike any previously observed comet, beginning significant outgassing at distances where solar system comets remain completely dormant. This early activation suggests a composition dominated by highly volatile materials that sublimate at lower temperatures than water ice. The steep brightening curve, with a power law exponent of -3.8, indicates rapidly increasing activity as the comet approaches the Sun. This behavior resembles dynamically old comets from our own Oort cloud, objects that have made multiple passages through the inner solar system and developed enhanced volatile transport networks. However, ATLAS is supposedly making its first approach to any star system since being ejected from its parent system millions or billions of years ago. The contradiction between fresh interstellar status and old comet behavior suggests either unusual formation conditions or modifications during its interstellar journey that created characteristics normally associated with solar exposure. Recent observations show that both dust and gas production rates increase exponentially with decreasing solar distance, following power laws with exponents approaching 9 for certain chemical species. This extreme sensitivity to solar heating implies either very shallow subsurface volatile reservoirs or enhanced heat transfer mechanisms within the nucleus. Multiple spacecraft throughout the solar system will attempt observations of ATLAS during its closest approach to the Sun, providing unprecedented multi-angle coverage of an interstellar visitor. These observations span different electromagnetic wavelengths and observational geometries, creating the most comprehensive data set ever collected for an object of this type. NASA's Parker Solar Probe, designed to study the Sun's corona, will observe ATLAS using its WISPR instrument during late September through early November. This timing covers the comet's perihelion passage and offers views from closer to the Sun than any other observatory can achieve. The Lucy mission, en route to study Jupiter's Trojan asteroids, may capture images of ATLAS from its unique position in the outer solar system. Similarly, NASA's Psyche mission, traveling toward the metal-rich asteroid 16 Psyche, passed close to ATLAS on September 4th, though no images have yet been released publicly. The most intriguing observations may come from ESA's Hera mission, launched to study the aftermath of NASA's DART impact on asteroid Dimorphos. Hera's instruments, designed for detailed surface mapping and composition analysis, could provide unprecedented views of ATLAS's nucleus structure during its approach phase. Several planned observations face significant technical challenges related to spacecraft positioning and communication constraints. JUICE, potentially offering the best views of ATLAS during peak activity, currently cannot transmit data at normal rates due to its proximity to the Sun, requiring antenna shielding. The spacecraft's main high-gain antenna serves as a heat shield during solar close approach, forcing communication through smaller backup antennas with severely limited bandwidth. This constraint means that any ATLAS observations may not reach Earth until February 2026, months after the comet has passed perihelion and begun fading. Europa Clipper faces similar challenges as it travels through the inner solar system toward its eventual Jupiter destination. The spacecraft's instruments are optimized for icy moon analysis rather than cometary observation, though its ultraviolet spectrographs may detect spectral signatures invisible to Earth-based telescopes. Coordination between multiple spacecraft observations requires precise timing and data correlation to maximize scientific return. The challenges of interplanetary communication, combined with the brief observational windows as ATLAS races through the inner solar system, demand careful planning and realistic expectations for data acquisition. The accumulating anomalies associated with ATLAS challenge several fundamental assumptions about interstellar objects and cometary science. The combination of unusual trajectory alignment, distinctive chemical composition, anomalous brightness behavior, mysterious color transformation, and unprecedented sunward glow creates a pattern that defies simple explanation. Some researchers have begun exploring whether Atlas represents a new class of interstellar object, perhaps formed under conditions not present in our solar systems. Region of the galaxy. The dominance of carbon dioxide over water, the early activation of outgassing, and the unusual nuclear composition might reflect formation around different types of stars with distinct chemical environments. The possibility that Atlas originates from the galaxy's thick disk opens questions about stellar nucleosynthesis in early galactic history. If this interpretation proves correct, the comet carries chemical signatures from stellar environments that existed when our galaxy was young, providing direct samples of ancient stellar processing. Alternative explanations range from conventional but unusual natural processes to scenarios that stretch the boundaries of current scientific understanding. The alignment with the ecliptic plane combined with the other anomalies has prompted some researchers to investigate whether Atlas might represent something other than a typical comet. As October progresses toward the 13th, Atlas will reach its closest approach to the Sun, marking the climax of its journey through our solar system. This perihelion, the comet's passage at approximately 1.4 astronomical units, places it between the orbits of Earth and Mars at its point of maximum solar heating. This relatively close perihelion presents a prime opportunity for scientific observation, as outgassing rates peak, revealing the comet's true nature. However, its position during this crucial period, on the opposite side of the Sun from Earth, renders ground-based observations incredibly difficult. Solar conjunction, when Atlas appears close to the Sun in Earth's sky, will make the comet completely unobservable from our planet during its most active phase. This unfortunate timing means the most dramatic aspects of Atlas's evolution may occur beyond the reach of even our most powerful Earth-based telescopes. Therefore, space-based observatories, including those orbiting Mars and other spacecraft throughout the solar system, become essential for maintaining continuous observation during this critical juncture. The Parker Solar Probe, specifically engineered to operate in an intense solar environment, may offer the only detailed observations of Atlas at perihelion. Following its perihelion passage, Atlas embarks on its lengthy journey back into interstellar space, a journey with no return to our solar system. Outbound observations, commencing in early November as the comet emerges from solar conjunction, will reveal the effects of intense solar heating on its nucleus and activity patterns. Many comets undergo dramatic transformations during perihelion passage. Some even fragment under thermal stress, while others develop new outgassing patterns that persist for months or years. Atlas's behavior during this outbound phase will provide critical insights into its internal structure and composition. This fading phase offers a unique opportunity to study how an interstellar object responds to intense solar heating and whether these conditions induce lasting modifications. Changes in brightness, spectral characteristics, or coma structure could reveal how thermal cycling impacts materials originating in other star systems. By early 2026, Atlas will have faded beyond the reach of most telescopes, returning to the interstellar medium carrying the modifications. Resulting from its solar encounter, the comet will traverse the void between stars for the next several million years, potentially carrying traces of Earth-based contamination or solar system signatures to distant regions of our galaxy. Atlas's brief visit prompts profound questions about the frequency and characteristics of interstellar visitors to our solar system. If such objects pass through regularly, as some models suggest, then our solar system exists within a constant stream of material from other star systems, fostering ongoing opportunities for chemical and potentially even biological exchange. The unusual properties of Atlas strongly suggest that interstellar objects might be far more diverse than our limited sample currently indicates. Each visitor bears unique signatures of its formation environment, potentially revealing details about stellar conditions throughout our galaxy's history and various regions of space. Future surveys, notably the Vera Rubin Observatory, soon to begin operation, will dramatically improve our ability to detect interstellar objects. Its wide field of view and sensitive instrumentation may reveal dozens of visitors similar to Atlas, creating a substantial database for comparative analysis. The European Space Agency's Comet Interceptor mission, specifically designed to study pristine comets and interstellar visitors, represents a significant advancement in exploration technology for these objects. Unlike sample return missions that require years of extensive planning, the Comet Interceptor will remain on standby, ready to investigate any suitable target detected with sufficient advance warning. The discovery of Atlas showcases how modern survey capabilities have revolutionized our ability to detect and study interstellar objects. The network of telescopes comprising the Atlas survey, coupled with data archives from the Zwicky Transient Facility and other surveys, provides comprehensive coverage, ensuring that few bright interstellar visitors will remain undetected. Sophisticated artificial intelligence and machine learning algorithms now automatically scan millions of astronomical images, identifying moving objects and unusual signatures that might suggest an interstellar origin. These systems process observational data far more rapidly than human astronomers, facilitating prompt follow-up observations while objects remain within reach. The integration of space-based and ground-based observatories creates multiple independent detection pathways, with instruments like the Transiting Exoplanet Survey Satellite, TESS, providing additional coverage to fill gaps in ground-based monitoring. This redundancy ensures that interstellar objects like Atlas can be detected and studied even if initially too faint for any single survey to detect. Advanced data sharing protocols enable the rapid dissemination of discovery information to observatories worldwide, facilitating coordinated follow-up observations that maximize scientific return. The Minor Planet Center's automated notification systems ensure that significant discoveries reach the global astronomical community within hours of initial detection. Each interstellar visitor contributes unique data to our expanding database of chemical compositions from other star systems. The unusual dominance of carbon dioxide in Atlas, combined with distinctive nickel signatures and the absence of expected iron, provides valuable insights into stellar nucleosynthesis and planetary formation processes in diverse galactic environments. Comparing Atlas with previous visitors like Oumuamua and Borisov and future interstellar objects will reveal whether common formation processes occur throughout our galaxy or whether each star system produces unique chemical signatures. The diversity observed so far indicates considerable variation in stellar environments and planetary system evolution. Spectroscopic databases compiled from multiple interstellar visitors may eventually allow us to determine the origins of objects through chemical fingerprinting. Different stellar populations throughout our galaxy should exhibit characteristic element ratios and molecular compositions that serve as signatures of their formation environments. The accumulating data also provides crucial input for theoretical models of galactic chemical evolution, stellar nucleosynthesis, and planetary system formation. Direct samples from other star systems offer unprecedented opportunities to test models that previously relied solely on astronomical observations and laboratory experiments. As Atlas traverses our solar system, it potentially accumulates contamination from solar wind particles, interplanetary dust, and even traces of Earth's atmosphere that escape into space. This acquired material will accompany the comet back into interstellar space, carrying chemical signatures of our solar system to distant regions of the galaxy. The possibility of biological contamination, while extremely improbable, raises intriguing questions about interstellar transfer of organic material. Earth's upper atmosphere contains microorganisms that could theoretically survive transfer to passing interstellar objects, although the harsh conditions of space render such survival highly unlikely. More significantly, Atlas may carry industrial signatures from human activity, including isotopic ratios, characteristic of nuclear technology and synthetic compounds produced only by technologically advanced civilizations. If the comet eventually encounters other star systems, these signatures could serve as evidence of technological activity in our solar system. Conversely, the possibility that Atlas carries signatures from its origin system drives much of the current research into the comet's composition and characteristics. Any unusual elements, isotopic ratios, or organic compounds could provide direct evidence of conditions around other stars or even biological processes in distant planetary systems. Statistical models suggest that objects like Atlas regularly pass through our solar system, perhaps several times per decade, although most remain too faint for detection with current technology. The Vera Rubin Observatory and other next-generation surveys will dramatically enhance our detection sensitivity, revealing a constant stream of interstellar visitors. Each new detection will add to our understanding of galactic populations, stellar system characteristics, and the frequency of planetary formation throughout our cosmic neighborhood. The accumulating data may reveal patterns in visitor characteristics that reflect the structure and evolution of our galaxy's stellar populations. Advanced mission concepts under development include rapid response spacecraft capable of intercepting interstellar objects with minimal advanced warning. These missions would carry sophisticated analytical instruments for detailed in situ studies, impossible from ground-based observations. The European Space Agency's Comet Interceptor represents the first such mission designed to rendezvous with a pristine comet or interstellar object for detailed investigation. Future missions may include sample return capabilities, bringing material from other star systems directly to Earth-based laboratories for comprehensive analysis. The study of Atlas demonstrates how rapidly evolving technology enhances our ability to investigate cosmic visitors. Advanced spectroscopic techniques, machine learning algorithms for data analysis, and coordinated multi-wavelength observations create research capabilities that surpass those available for previous interstellar objects. Future technological developments will further expand our investigative tools. Next-generation space telescopes, including successors to the James Webb Space Telescope, will provide unprecedented spectroscopic resolution for studying faint interstellar objects. Advanced coronagraph systems may enable detailed observations even when objects appear close to the sun. Artificial intelligence systems trained on vast databases of astronomical observations will identify subtle patterns and anomalies that human researchers might miss. These systems may detect evidence of unusual composition, artificial origin, or exotic physics in ways that complement traditional analytical approaches. The integration of quantum sensing technologies, advanced materials science, and sophisticated computational modeling creates new possibilities for understanding objects that spend only brief periods within observational range. These tools may reveal secrets of interstellar visitors that remain hidden with current technology. Atlas's passage through our solar system raises profound questions about our place in the galaxy and the nature of the cosmic environment surrounding Earth. We exist within a dynamic system where material constantly flows between star systems, creating connections across vast distances and timescales. The possibility that some interstellar visitors might be artificially created objects, while scientifically controversial, necessitates consideration of how we might recognize evidence of other technological civilizations. The accumulating anomalies associated with Atlas, while likely natural in origin, illustrate the challenges of distinguishing artificial from natural phenomena. The chemical diversity observed in interstellar objects suggests that our solar system represents just one example among countless variations throughout the galaxy. The conditions that enabled life on Earth may be common, rare, or unique, depending on how frequently the chemical Ingredients for biology appear in other stellar systems. The brief windows available for studying interstellar visitors emphasize both our current limitations and the vast scope of cosmic phenomena. Beyond our detailed investigation, each visitor carries information about distant regions of space and time. But our fleeting opportunities for investigation capture only fragments of these cosmic stories. The international collaboration required to study Atlas demonstrates how modern astronomy transcends national boundaries and institutional limitations. Observatories across 6 continents coordinate observations, sharing data through sophisticated networks that enable real-time analysis of rapidly evolving phenomena. The Atlas survey system exemplifies this global approach, with telescopes in Chile, South Africa, and Hawaii providing continuous monitoring of the entire visible sky. When the Chilean facility first detected Atlas on July 1st, the discovery triggered automated alerts that reached observatories worldwide within minutes. Ground-based networks now integrate seamlessly with space-based assets, creating observation campaigns that span from radio telescopes on Earth's surface to ultraviolet spectrographs beyond our atmosphere. The James Webb Space Telescope's observations of Atlas coordinate with simultaneous measurements from the Hubble Space Telescope, creating multi-wavelength datasets impossible to achieve with any single instrument. Amateur astronomers contribute significantly to these collaborative efforts with citizen science. Networks like the Unistellar system providing distributed observations that complement professional facilities. Michael Jerger and Gerald Raymond's detection of the green transformation exemplifies how dedicated amateur observers often capture crucial developments that professional surveys might miss. The data-sharing protocols developed for Atlas observations will establish templates for studying future interstellar visitors. Standardized formats, rapid communication systems, and coordinated observing schedules maximize scientific return from objects that remain accessible for only brief periods. Analyzing the deluge of data generated by Atlas observations requires computational resources and algorithmic sophistication that pushes current technology to its limits. Each night of observations from major telescopes generates terabytes of raw data, requiring processing, calibration, and analysis before scientific interpretation becomes possible. Machine learning. Algorithms trained on vast databases of cometary observations attempt to identify patterns and anomalies in Atlas's behavior that human researchers might overlook. These systems analyze brightness, variations, spectral changes, and morphological evolution across thousands of images with consistency and speed impossible for manual analysis. Advanced atmospheric modeling incorporates data from multiple spacecraft to understand how Atlas's outgassing interacts with the solar wind and interplanetary magnetic field. These simulations require supercomputer resources to model the complex physics of gas and dust dynamics in the harsh environment of interplanetary space. Orbital mechanics calculations trace Atlas's trajectory back through millions of years of galactic motion, accounting for gravitational perturbations from countless stellar encounters during its interstellar journey. These computations reveal probable origin regions while highlighting the fundamental uncertainties inherent in reconstructing ancient cosmic paths. The integration of observational data with theoretical models creates feedback loops that refine our understanding of cometary physics, galactic dynamics, and the properties of interstellar space. Each new measurement constrains theoretical possibilities while revealing additional complexities that require further investigation. High-resolution spectroscopy of Atlas may eventually reveal isotopic ratios that provide direct information about nuclear processes in its parent star system. Different stellar masses and evolutionary stages produce characteristic isotopic signatures that serve as fingerprints of their nuclear furnaces. The carbon-to-nitrogen ratio in Atlas's coma already suggests formation conditions distinct from our solar system's environment. As spectroscopic precision improves, Additional elemental ratios may reveal whether the comet formed around a star with different mass, age, or metallicity than our Sun. Isotopic analysis requires extremely high spectral resolution and signal-to-noise ratios that challenge current observational capabilities. The faintness of Atlas, combined with its rapid motion across the sky, limits exposure times and complicates the precise measurements needed for isotopic determination. Future space-based spectrographs with enhanced sensitivity and stability may enable detailed isotopic analysis of interstellar visitors, providing direct measurements of stellar nucleosynthesis processes throughout our galaxy. These data would test theories of galactic chemical evolution with unprecedented precision. The potential discovery of isotopic ratios impossible to produce in any known stellar environment would revolutionize our understanding of nuclear physics or suggest exotic formation scenarios beyond current theoretical frameworks. Such findings would rank among the most significant discoveries in modern astronomy. As Atlas approaches perihelion, thermal modeling attempts to predict how solar heating will affect its nuclear structure and composition. The unusual activity patterns observed so far suggest internal characteristics significantly different from typical solar system comets. Thermal penetration into the nucleus depends on factors including porosity, composition, thermal conductivity, and rotation rate, most of which remain poorly constrained for Atlas. The early onset of activity suggests either very low thermal inertia or a composition dominated by highly volatile materials. Subsurface temperature profiles control the timing and intensity of outgassing as different chemical species reach sublimation temperatures at various depths within the nucleus. The steep activity increase observed in Atlas implies rapid thermal penetration or unusually shallow volatile reservoirs. Computer simulations model various nucleus compositions and structures to match observed brightness and spectral evolution. These models suggest that Atlas may have a layered structure with different volatile distributions at various depths, possibly reflecting its formation history or modifications during interstellar travel. The dramatic color change from red to green indicates thermal activation of previously dormant chemical processes or structural changes that expose new material to solar radiation. Understanding these transformations requires detailed knowledge of how heat propagates through porous, heterogeneous materials under space conditions. Atlas travels through the complex magnetic environment of interplanetary space where the solar wind carries embedded magnetic fields that interact with the charged particles in the comet's coma. These interactions create phenomena that may be detectable with appropriate instrumentation. Charged dust grains and ions in the coma respond to magnetic forces, potentially creating asymmetric structures or preferred outflow directions that depend on the local magnetic field orientation. Such effects might explain some of the unusual morphological features observed in Atlas's coma. The Parker Solar Probe, designed to study solar wind properties and magnetic field structure, may detect signatures of Atlas's interaction with the interplanetary environment during their close encounter near perihelion. These measurements could reveal how interstellar objects modify local space conditions. Magnetic field measurements from spacecraft throughout the solar system provide context for understanding how Atlas's passage affects the broader interplanetary environment. The comet's outgassing creates a small but detectable perturbation in the solar wind that propagates across millions of kilometers. Advanced plasma physics simulations model the complex interactions between the solar wind, interplanetary magnetic field, and Atlas's coma to predict observable signatures and understand the physical processes involved. These models require sophisticated numerical techniques and massive computational resources. The unusual polarization properties of Atlas suggest that its dust particles differ significantly from those found in solar system comets. These differences may reflect formation conditions, interstellar modifications, or compositional variations that affect particle structure and optical properties. Dust grain analysis using scattered light measurements attempts to determine particle size distributions, compositions, and morphologies that control how Atlas interacts with solar radiation. The deep negative polarization observed suggests particles with distinctive optical characteristics. Radiation pressure from the Sun accelerates dust particles away from Atlas's nucleus, creating the visible coma and potentially contributing to tail formation. The efficiency of this process depends on particle size, composition, and optical properties that remain poorly understood for interstellar material. Advanced scattering models incorporate various particle compositions and structures to match observed polarization and brightness measurements. These models suggest that Atlas may eject particles with complex morphologies or exotic compositions not found in typical cometary dust. The interaction between charged dust particles and the interplanetary magnetic field creates additional complexity in dust dynamics, potentially leading to asymmetric dust distributions or preferred ejection directions that contribute to the unusual morphological features observed in Hubble images. The spectroscopic signature of Atlas continues evolving as changing solar heating activates different chemical processes within its nucleus. This evolution provides a real-time view of how interstellar material responds to stellar radiation. Early observations dominated by carbon dioxide emission are giving way to more complex spectra as additional molecular species reach sublimation temperatures. The dramatic increase in cyanide production represents just one example of how changing conditions activate new chemistry. High-resolution spectroscopy reveals Doppler shifts in emission lines that indicate expansion velocities and outflow patterns within the coma. These measurements constrain models of gas dynamics and help distinguish between different outgassing mechanisms. The sudden appearance of green emission suggests activation of chemistry involving carbon-bearing molecules, though the specific compounds responsible remain uncertain. Continued spectroscopic monitoring may identify the molecules causing this dramatic color change. Future observations will track how Atlas's spectrum evolves through perihelion passage and into the outbound phase, revealing how thermal cycling affects chemical processes in material formed around other stars. This temporal evolution provides unique insights into interstellar chemistry. Intense solar heating during perihelion passage poses a significant risk of nuclear fragmentation for Atlas, potentially destroying our opportunity to study an intact interstellar object. Many comets experience structural failure when thermal stresses exceed their mechanical strength. The unusual activity patterns and rapid brightening of Atlas may indicate internal structural modifications that affect its resistance to thermal stress. Early outgassing might have created internal fractures or weakened zones that become failure points under intense heating. Monitoring for signs of fragmentation requires high-resolution imaging that can detect small pieces separating from the main nucleus. Such observations demand excellent seeing conditions and sophisticated image processing to distinguish genuine fragments from temporary brightness variations. The Hubble Space Telescope's exceptional angular resolution makes it the premier instrument for detecting potential fragmentation events. However, the comet's position near the Sun during perihelion limits observational opportunities when fragmentation risk is highest. Fragmentation would dramatically alter Atlas's subsequent evolution, potentially creating a debris stream that provides multiple targets for spectroscopic analysis while simultaneously reducing the intensity of individual fragments below detection thresholds. The specific physical processes driving Atlas's unusual outgassing patterns remain poorly understood despite extensive observational and theoretical investigation. The early activation, rapid brightening, and unusual chemical composition suggest mechanisms different from typical cometary sublimation. Direct sublimation from the nuclear surface cannot account for the observed activity levels at large solar distances, suggesting either enhanced heat transfer within the nucleus or chemistry involving more volatile species than water ice. Carbon dioxide sublimation occurs at lower temperatures, but requires unusually high concentrations to explain the observations. Subsurface sublimation followed by gas transport through porous networks within the nucleus could explain some unusual features. However, this mechanism requires specific structural characteristics that may not apply to interstellar objects with different formation historique. Explosive outgassing triggered by phase transitions, crystallization events, or chemical reactions could produce the rapid brightness variations observed in Atlas. Such processes might be activated by solar heating, but operate through mechanisms distinct from simple sublimation. The anomalous sunward extension of scattered light suggests directed outgassing or unusual particle dynamics that current models struggle to explain. Understanding this phenomenon requires new theoretical frameworks that may apply to interstellar objects but not solar system. Comets. The growing catalog of chemical species detected in Atlas provides an increasingly detailed picture of its composition and the conditions present in its formation environment. Each new molecular identification adds constraints to models of stellar nucleosynthesis and planetary formation processes. Water, carbon dioxide, carbon monoxide, cyanide, and various organic compounds create a chemical inventory that differs significantly from typical solar system comets. The dominance of carbon dioxide over water particularly stands out as unusual for objects formed in our cosmic neighborhood. Trace species detection requires extremely sensitive spectroscopic techniques that push observational capabilities to their limits. Each additional molecular identification provides crucial information about formation conditions and evolutionary history. The absence of certain expected species may be as informative as positive detections, suggesting formation. Environments that lack typical cometary chemistry or evolutionary processes that have modified the original composition through chemical reactions or selective loss. Comparison with laboratory. Experiments on ice chemistry under various temperature and radiation conditions helps interpret the observed molecular inventory and constrain the physical conditions experienced by Atlas during its formation and interstellar journey. Understanding the internal structure of Atlas's nucleus presents fundamental challenges due to its small size and great distance from Earth. Current observations provide only indirect constraints on density, porosity, composition, and structural characteristics. The relationship between nuclear size and observed activity suggests either very high volatile content or enhanced heat transfer efficiency compared to typical comets. These characteristics might reflect formation conditions or structural modifications during interstellar travel. Thermal modeling attempts to infer internal structure from observed outgassing patterns. However, multiple structural scenarios can produce similar observational signatures, distinguishing between different models requires additional constraints from future observations. Rotation period determination could provide information about nuclear shape and density distribution, though detecting brightness variations from such a distant object challenges current observational capabilities. Long-term photometric monitoring may eventually reveal rotational signatures. The unusual polarization. Properties suggest surface or near-surface characteristics that differ from typical cometary nuclei, possibly indicating compositional variations, structural modifications, or exotic materials not found in solar system objects. The chemical composition and physical characteristics of Atlas provide clues about the stellar environment where it formed billions of years ago. These ancient signatures preserve information about stellar nucleosynthesis and planetary system evolution in different galactic contexts. The unusually high carbon dioxide content suggests formation in a stellar system with different carbon-to-oxygen ratios than our solar system, possibly around stars with different masses, ages, or metallicities. Such variations affect the chemical inventory available for planetary formation. Isotopic ratios, when eventually determined, will provide direct information about nuclear processes in the parent star and constrained models of stellar evolution and galactic chemical evolution. These measurements represent our most direct access to stellar nucleosynthesis beyond our solar system. The apparent age of Atlas, potentially billions of years, means it formed when our galaxy had a different chemical composition and stellar populations than today. Studying this ancient visitor provides insights into cosmic chemical evolution over galactic timescales. Comparing Atlas with other interstellar objects and solar system comets will reveal whether its unusual characteristics reflect typical conditions in other stellar systems or represent an exotic formation scenario. The unusual characteristics of Comet Atlas, a rare interstellar visitor, present a unique opportunity to advance our understanding of cometary physics, interstellar environments, and the evolution of planetary systems. Its trajectory, closely aligned with the galactic plane, suggests formation within the thick disk of stars, a region distinct from our Sun's location in the thin disk. This implies a different origin environment and stellar population than previously studied comets. Sophisticated models of galactic dynamics and stellar kinematics are required to trace its path back through millions of years of galactic motion, aiming to identify its origin star system. Gravitational perturbations from stellar encounters during its interstellar journey have undoubtedly altered its original trajectory, increasing the difficulty of pinpointing its precise origin, even with statistical analyses of likely source regions. The high velocity of Atlas relative to our solar system strongly suggests either ejection from a high-velocity stellar system or significant acceleration through gravitational interactions during its interstellar passage. Further astrometric measurements will refine our understanding of its orbital parameters and refine trajectory reconstructions, potentially providing additional clues about its origin, region, and evolutionary history. The extensive observational campaign dedicated to Atlas establishes a new standard for studying transient astronomical phenomena, highlighting the power of modern coordinated astronomy. The techniques developed and refined through this study will undoubtedly benefit future investigations of similar objects. Archive data from multiple sky surveys, spanning months before its official discovery, underscore the vital importance of maintaining comprehensive sky monitoring systems. These archives are crucial for reconstructing the object's evolution during periods when no targeted observations were conducted. The integration of both professional and amateur observations created an observational network with an unprecedented level of geographic and temporal coverage, exceeding the capabilities of any single institution. The contributions from citizen scientists proved particularly invaluable in monitoring this rapidly evolving phenomenon. The standardized data formats and rapid communication protocols established for Atlas observations will facilitate future coordinated campaigns, ensuring more efficient utilization of limited observational windows for transient objects. The lessons learned from observing Atlas directly inform the design of future survey systems and spacecraft missions, highlighting the necessary observational capabilities to maximize the scientific return from fleeting encounters with interstellar visitors. The unusual characteristics of Atlas challenge established theoretical frameworks concerning cometary physics. Traditional sublimation models based solely on water-ice physics are insufficient to explain its early activity and rapid brightening, demanding the incorporation of more volatile species and complex thermal processes into these models. The sunward extension of scattered light directly contradicts our current understanding of radiation pressure and dust dynamics around comets, suggesting either exotic particle properties or entirely novel physical processes that have never before been observed or even theoretically predicted. Advanced computational models, incorporating complex chemistry, multi-component physics, and three-dimensional structures, are being developed in an attempt to reproduce the full range of observed phenomena. These advanced models demands substantial computational resources and sophisticated numerical techniques. The development of theoretical frameworks capable of adequately explaining Atlas's behavior will significantly advance our general understanding of cometary physics and better prepare us for the investigation of future interstellar visitors that may exhibit similarly unusual characteristics. The discovery rate of interstellar objects has risen dramatically with improvements in survey capabilities, suggesting that these cosmic wanderers may be far more common than previously believed. Statistical analysis is currently underway to estimate the true population and frequency of these interstellar objects. The detection of 3 confirmed interstellar objects within just 8 years implies a much larger, undetected population of fainter objects, currently beyond the reach of our current technology. Advanced surveys currently coming online will significantly increase our detection sensitivity, revealing the true abundance of interstellar visitors. Population models extrapolate from existing detections to estimate the total number of interstellar objects passing through our solar system annually. These models suggest that numerous objects exceeding 100 meters in diameter may transit our cosmic neighborhood each year. The observed size distribution of interstellar objects shows a strong observational bias toward larger, more active specimens. Future surveys with enhanced sensitivity will determine whether smaller interstellar objects follow similar size distributions to those observed for solar system comets and asteroids. Long-term monitoring of interstellar object detection rates will provide crucial constraints on models of galactic stellar populations and planetary system evolution, ultimately offering insights into the efficiency of planetary formation processes throughout our cosmic neighborhood. The short notice provided by current detection systems significantly limits our ability to launch dedicated missions to study interstellar objects in detail. Future mission concepts must incorporate rapid response capabilities or remain on standby for suitable targets. The European Space Agency's Comet Interceptor mission represents a significant step forward as the first spacecraft specifically designed for studying pristine comets and potentially interstellar objects. Its mission architecture allows for the investigation of targets with minimal advanced warning. Advanced propulsion concepts currently under development could enable even more ambitious interstellar object missions, including the possibility of sample return capabilities that would bring material from other star systems directly to Earth-based laboratories for comprehensive analysis. Rapid response mission concepts require pre-positioned spacecraft, advanced propulsion systems, and streamlined mission planning processes that can be rapidly activated when suitable targets are identified. These capabilities demand entirely new approaches to space mission design and implementation. The scientific return from dedicated interstellar object missions would far surpass that achievable from remote observations alone, providing detailed compositional analysis, internal structure determination, and direct sampling of material from other stellar systems. The discovery and unusual behavior of Comet Atlas have captivated the public imagination in a way rarely achieved by typical astronomical discoveries. The combination of mystery, potential implications, and striking visual observations creates compelling narratives that resonate with a diverse range of audiences. Social media coverage of Atlas demonstrates both the benefits and challenges of rapid information dissemination in the digital age. Accurate scientific information often competes with sensationalized claims and speculative interpretations that can significantly confuse public understanding. The case of Atlas exemplifies how complex astronomical information can be misinterpreted and amplified through social media algorithms, often prioritizing engagement over accuracy. Distinguishing between legitimate scientific discoveries and viral misinformation demands careful attention to sources and context. The educational opportunities presented by Atlas enable astronomy outreach, connecting current research with fundamental questions about our place in the universe. Its interstellar origin provides tangible connections to concepts that might otherwise remain abstract for the general public. The significant public interest in Atlas may well influence funding priorities and mission planning for future interstellar object investigations, highlighting the importance of maintaining the necessary capabilities for studying these rare cosmic visitors. The investigation of Atlas showcases the rapid advancement of technology that is enhancing our ability to study faint, fast-moving objects throughout the solar system. Each new technological capability opens up new avenues for scientific investigation. Advanced detector technologies now enable spectroscopic observations of objects too faint for previous generation instruments, a significant improvement that particularly benefits the study of distant, low-activity objects like Atlas during its approach phase. Machine learning algorithms, trained on vast astronomical databases, can identify subtle patterns and anomalies that might be easily overlooked by human researchers. These tools prove particularly valuable for analyzing the complex, rapidly evolving datasets generated by Atlas observations. Improved computational capabilities allow for sophisticated modeling of complex physical processes, ensuring that theoretical frameworks can keep pace with the increasingly detailed observational constraints provided by modern instruments. The integration of ground-based and space-based observations creates synergistic capabilities that exceed the sum of individual contributions, enabling investigations that would be impossible with any single observational platform. The unusual characteristics revealed by Atlas suggest that future interstellar visitors may display similarly surprising properties, potentially challenging our existing understanding of these cosmic wanderers. Each new detection adds to our growing appreciation of their diversity. Advanced survey systems currently coming online will detect interstellar objects at much greater distances, providing longer lead times for detailed study and potentially enabling spacecraft intercept missions with adequate advanced warning. The accumulating database of interstellar object properties will facilitate statistical studies that will reveal patterns and correlations invisible in smaller sample sizes. These analyses may identify common characteristics or formation mechanisms applicable throughout our galaxy. Future space-based telescopes with enhanced sensitivity and spectroscopic capabilities will enable detailed chemical analyses of interstellar objects, potentially revealing isotopic signatures and exotic compounds that provide direct information about stellar nuclear synthesis processes. The development of rapid response spacecraft capabilities will fundamentally transform our ability to study interstellar objects in detail, enabling comprehensive understanding rather than the limited snapshots currently possible with remote observations. In a galactic context, Atlas represents a single sample from the vast population of small bodies ejected from planetary systems throughout our galaxies. History. Understanding its characteristics provides valuable insights into planetary formation processes and stellar evolution across diverse galactic environments. The estimated age of Atlas, potentially billions of years, means it has witnessed galactic evolution over cosmologically significant timescales. Its composition preserves information about stellar nuclear synthesis and chemical conditions from earlier epochs in our galaxy's history. Comparing Atlas with other interstellar objects and solar system bodies reveals the remarkable diversity of formation environments and evolutionary processes operating throughout our cosmic neighborhood. Each object represents a unique experiment in planetary formation. The trajectory of Atlas suggests an origin in the thick disk stellar population, providing our first direct sample of material from this ancient galactic component. Future studies will determine whether thick disk objects display systematically different compositions than their thin disk counterparts. Statistical models of galactic structure and stellar evolution incorporate data from interstellar objects to constrain theories of galactic chemical evolution and planetary system formation efficiency across different stellar populations. Each molecular species detected in Atlas provides constraints on the temperature, pressure, and chemical conditions present during its formation billions of years ago. The growing inventory of identified compounds is creating an increasingly detailed picture of its origin environment. The unusual carbon dioxide dominance may reflect formation around stars with different carbon-to-oxygen ratios than our Sun, possibly indicating different stellar masses, evolutionary stages, or galactic chemical environments at the time of the comet's formation. Organic compound detection would provide crucial information about the prevalence of carbon chemistry in other stellar systems, and potentially offer insights into the distribution of life's chemical precursors throughout our galaxy. Isotopic measurements, when eventually achieved, will provide direct constraints on nuclear processes in the parent star system and test models of stellar nuclear synthesis that currently rely entirely on astronomical observations and theoretical calculations. The temporal evolution of Atlas's chemical signature as it approaches and recedes from the Sun reveals how thermal processing affects interstellar material and provides insights into the physical structure and composition of its nucleus. Complex interactions develop between Atlas's coma and the local electromagnetic environment as it releases gas and dust into the surrounding space. These processes create observable phenomena that provide additional diagnostic tools for understanding the comet's behavior and composition. The solar wind, carrying embedded magnetic fields and charged particles, encounters the neutral gases surrounding Atlas and initiates chemical reactions that produce ionized species, detectable through characteristic emission lines. These interactions create a secondary chemistry, distinct from the sublimation processes occurring at the nuclear surface. Ultraviolet radiation from the Sun photodissociates molecular species in the coma, breaking apart complex compounds and creating fragments that may not exist under terrestrial conditions. This photochemistry produces short-lived species that are challenging to detect but provide crucial information about the parent molecules from which they derive. The Parker Solar Probe's upcoming observations of Atlas will occur within the solar wind environment, where these interactions reach maximum intensity. The spacecraft's plasma instruments may detect perturbations in the solar wind caused by the comet's passage, revealing information about outgassing rates and coma composition invisible to remote observations. Magnetohydrodynamic simulations model the complex interactions between the solar wind, the interplanetary magnetic field, and Atlas's expanding coma to predict observable signatures and understand the underlying physics. These calculations require sophisticated numerical methods and massive computational resources to capture the relevant physical processes. The unusual polarization. Characteristics of Atlas suggest that its dust particles possess properties significantly different from those found in solar system comets. Understanding these differences provides insights into formation conditions and evolutionary processes in other stellar systems. Light scattering measurements attempt to determine particle size distributions, refractive indices, and morphologies that control how Atlas interacts with solar radiation. The deep negative polarization observed indicates particles with distinctive optical characteristics that may reflect exotic compositions or unusual structures. Laboratory experiments on analogous materials help interpret the polarization measurements by providing controlled studies of how different particle compositions and structures affect light scattering properties. These experiments reveal that the observed polarization signature requires either unusual compositions or particle morphologies not typical of terrestrial materials. Advanced electromagnetic scattering calculations model various particle compositions, sizes, and shapes to match observed polarization and brightness measurements. These models suggest that Atlas may eject particles with complex internal structures or surface properties that reflect formation in different chemical environments. The temporal evolution of polarization properties as Atlas approaches perihelion may reveal changes in particle characteristics caused by thermal processing or the activation of different outgassing sources within nucleus. Such evolution would provide unique Insights into how solar heating affects interstellar material. The intense thermal stresses experienced during perihelion passage pose significant risks for nuclear fragmentation, potentially fundamentally altering Atlas's subsequent evolution. Historical observations of comet breakup events provide valuable context for assessing this possibility. Thermal expansion and contraction cycles can create internal fractures that weaken the nuclear structure, making it more susceptible to disruption from gas pressure or rotational stresses. The porous, heterogeneous structure typical of cometary nuclei makes them particularly vulnerable to thermal stress fracturing. Sublimation pressure from trapped gases within the nucleus can exceed the mechanical strength of the surrounding material, leading to explosive outgassing events that fragment portions of the nucleus. Such events often produce dramatic brightness increases, followed by the appearance of multiple components in high-resolution images. Monitoring Atlas for signs of fragmentation requires high angular resolution imaging capable of detecting small pieces separating from the main nucleus. The Hubble Space Telescope provides the best available capability for such observations, though the comet's position relative to the Sun limits observational opportunities during the highest risk period. Mathematical models of nuclear structure and thermal evolution attempt to predict fragmentation probability based on estimated composition, porosity, and mechanical properties. These models incorporate laboratory measurements of ice mechanical properties and thermal expansion coefficients under space conditions. A detailed comparison between Atlas and the two previously observed interstellar objects reveals both similarities and crucial differences that illuminate the diversity of these cosmic visitors. Each object represents a unique sample from different stellar environments and evolutionary histories. Oumuamua displayed no detectable outgassing, despite showing non-gravitational acceleration, suggesting either very low volatile content or unusual physical properties that prevented gas detection. Its elongated shape and rapid rotation created challenges for theoretical interpretation that remain unresolved. Borisov appeared more similar to typical solar system comets, with clearly detectable water vapor and dust emission that followed expected patterns for increasing solar heating. However, its chemical composition showed subtle differences that indicated formation in a different stellar environment. Atlas combines characteristics from both previous visitors while displaying unique features not observed in either predecessor. The early activity, unusual chemical composition, rapid brightening, and anomalous morphology create a distinctive profile that expands our understanding of interstellar object diversity. Statistical analysis of the small sample of known interstellar objects suggests that each represents a different class or formation environment, implying enormous diversity in the population of objects wandering between stars. Future detections will test whether this apparent diversity reflects true population characteristics or observational selection effects. The accumulating data from multiple interstellar objects enable comparative studies that may reveal common formation mechanisms or evolutionary processes while highlighting the unique characteristics that distinguish objects from different stellar systems. Understanding the internal structure and composition of Atlas requires sophisticated theoretical models that incorporate observational constraints while accounting for the inherent uncertainties in studying such distant, small objects. Thermal models attempt to reproduce observed outgassing patterns by varying nucleus composition, porosity, thermal conductivity, and structural characteristics. These models reveal that multiple parameter combinations can produce similar observational signatures, highlighting the challenges of uniquely determining internal properties. The early onset of activity suggests either very high volatile content or enhanced heat transfer mechanisms that allow solar heating to penetrate deeply into the nucleus, even at large distances from the Sun. Such characteristics might reflect formation conditions or structural modifications during interstellar travel. Layered models, incorporating different volatile distributions at various depths within the nucleus, attempt to explain the complex temporal evolution of Atlas's activity. These models suggest that thermal penetration progressively activates different chemical reservoirs as the comet approaches perihelion. Advanced computational techniques enable three-dimensional modeling of nucleus structure with realistic heterogeneity, porosity variations, and complex chemical distributions. These simulations require substantial computational resources but provide detailed predictions for comparison with observations. The extreme velocity of Atlas relative to our solar system provides crucial information about its origin and evolutionary history. Objects ejected from nearby stellar systems should display velocities related to the kinematics of their parent stars and the efficiency of ejection mechanisms. Stellar encounter modeling attempts to reproduce Atlas's observed velocity through gravitational interactions with massive objects during its interstellar journey. These calculations reveal that multiple stellar encounters could modify the original ejection velocity and complicate efforts to identify the parent system. The alignment of Atlas's trajectory with the galactic plane suggests a possible origin in the thick disk stellar population, which displays different kinematic characteristics than the thin disk region where our Sun resides. This alignment provides statistical constraints on probable origin regions. Galactic orbit calculations trace Atlas's motion through the galaxy's gravitational field over millions of years, accounting for the complex dynamics of stellar systems embedded within the galactic potential. These computations reveal probable paths and highlight regions where the comet may have originated. The high velocity also indicates that Atlas will escape our solar system with substantial kinetic energy, carrying it into interstellar space, where it may eventually encounter other stellar systems and potentially influence their chemical evolution through cross-contamination. Studying Atlas presents numerous technical challenges that push current observational capabilities to their limits. The combination of faintness, rapid motion, and limited observational windows demands innovative approaches and careful coordination between multiple facilities. Tracking rapidly moving objects requires sophisticated telescope control systems that can accurately follow predicted trajectories while maintaining precise pointing for long-exposure spectroscopy. Small errors in orbital prediction can result in the target moving outside the telescope field of view during extended observations. Atmospheric turbulence, particularly, affects observations of faint, distant objects like Atlas, requiring excellent seeing conditions or adaptive optic systems to achieve the resolution needed for detailed morphological studies. Many planned observations depend on favorable weather conditions that cannot be guaranteed. The comet's position relative to the Sun creates additional complications, with solar conjunction rendering ground-based observations impossible during the most scientifically interesting period around perihelion. Space-based observatories become crucial for maintaining observational coverage during this critical phase. Coordinating observations between multiple facilities across different time zones requires careful scheduling and communication to ensure that data collection proceeds efficiently. Despite equipment failures, weather delays, or other unforeseen complications that commonly affect astronomical observations, advanced spectroscopic analysis of Atlas requires sophisticated techniques that can extract weak signals from complex backgrounds while accounting for the comet's rapid motion and varying observational conditions. High-resolution spectroscopy attempts to resolve individual emission lines from different molecular species, enabling precise velocity measurements and abundance determinations that constrain models of coma chemistry and dynamics. Such observations require large telescopes and extended exposure times. Multi-wavelength spectroscopy, spanning ultraviolet, visible, and infrared regions, provides comprehensive coverage of different molecular transitions and electronic states. Each wavelength range offers unique diagnostic capabilities for identifying specific chemical species and physical conditions. Doppler shift measurements of emission lines reveal gas expansion velocities and outflow patterns within the coma, providing information about the physical processes driving outgassing and the structural characteristics of the nucleus. These measurements require extremely precise wavelength calibration. Time-resolved spectroscopy tracks rapid changes in emission line intensities and ratios that may indicate variable outgassing, chemical reactions, or structural modifications within nucleus. Such observations demand continuous monitoring over extended periods with consistent instrumental setup. Polarization spectroscopy examines how the polarization state of emission lines varies with observational geometry and molecular characteristics, providing additional constraints on physical conditions and chemical processes that complement intensity measurements. The changing chemical signature of Atlas as it approaches perihelion provides real-time observations of how thermal processing affects interstellar material and activates previously dormant chemical reservoirs within the nucleus. Early observations, dominated by carbon dioxide emission, are progressively supplemented by additional molecular species as increasing solar heating reaches deeper into the nucleus and activates more volatile components. This evolution reveals the chemical stratification within the nucleus. The dramatic increase in cyanide production represents just one example of how changing thermal conditions activate new chemistry. The steep power law dependence on solar distance suggests either unusual chemical kinetics or structural characteristics that amplify thermal effects. Organic molecule detection becomes increasingly likely as thermal processing breaks down complex compounds and releases simpler fragments detectable through characteristic emission signatures. Such detections would provide crucial information about carbon chemistry in other stellar systems. The temporal sequence of chemical activation may reveal information about nucleus structure and formation history, with different chemical reservoirs becoming accessible as thermal penetration reaches various depths within the heterogeneous nucleus. Understanding how Atlas's chemistry evolves through perihelion passage and into the outbound phase will provide insights into how thermal cycling affects materials formed in other stellar systems and may reveal chemical processes unique to interstellar objects. The unusual sunward extension of scattered light around Atlas suggests particle acceleration or transport mechanisms that differ from typical cometary processes. Understanding these mechanisms requires careful analysis of particle dynamics in a complex electromagnetic environment surrounding the comet. Radiation pressure from solar photons normally accelerates dust particles away from the sun, creating the familiar anti-solar tail structure observed in most comets. The apparent reversal of this effect in Atlas challenges our understanding of particle physics in cometary environments. Electromagnetic effects involving charged dust grains and the interplanetary magnetic field could potentially create unusual particle trajectories that contribute to the observed sunward extension. Such effects depend on particle size, charge state, and local magnetic field conditions. Gas drag forces from expanding neutral gases in the coma can influence particle motion, particularly for small grains that couple efficiently to gas flows. Complex gas dynamics, driven by non-uniform outgassing, could create particle transport patterns that differ from simple radiation pressure acceleration. Electrostatic charging of dust particles in the solar wind environment creates additional forces that may contribute to unusual particle trajectories. The balance between gravitational, electromagnetic, and radiation pressure forces determines particle motion and observable signatures. Advanced particle dynamics simulations, incorporating realistic electromagnetic environments and complex outgassing patterns, attempt to reproduce the observed morphological features and understand the underlying physical processes responsible for the unusual sunward extension. Solar heating of Atlas creates temperature gradients within the nucleus that drive sublimation and outgassing at various depths below the surface. Understanding these thermal processes requires detailed modeling of heat transfer through porous, heterogeneous materials under space conditions. Thermal diffusion calculations predict how solar heating penetrates into the nucleus as a function of thermal conductivity, porosity, and composition. These models reveal that typical cometary materials require substantial solar heating before interior temperatures reach sublimation thresholds for common ices. The early activity observed in Atlas suggests either unusually efficient heat transfer or a composition dominated by species that sublimate at lower temperatures than water ice. Carbon dioxide and carbon monoxide both sublimate at temperatures well below water, potentially explaining the early onset of activity. Thermal modeling must account for the complex feedback between sublimation and heat transfer as gas production removes latent heat while creating pathways for enhanced thermal conduction. These coupled processes create nonlinear behavior that complicates theoretical predictions. Subsurface temperature. Monitoring through thermal emission measurements provides observational constraints on thermal models and helps distinguish between different theoretical scenarios. The investigation of Oumuamua's successor, Atlas, reveals a complex interplay between diverse scenarios concerning its nuclear structure and composition. These observations demand the use of highly sensitive infrared instruments and meticulous subtraction of reflected sunlight. The thermal evolution of Atlas during its perihelion passage will serve as a crucial test for existing theoretical models, potentially revealing unique thermal behavior specific to interstellar objects. These objects likely possess vastly different formation histories and structural characteristics compared to comets originating within our solar system. The determination of Atlas's rotation period presents significant observational hurdles due to its small size, considerable distance, and a low amplitude of its brightness. Variations. However, a successful determination would yield critical insights into the shape, density distribution, and structural integrity of its nucleus. Photometric monitoring endeavors to detect periodic brightness fluctuations arising from the rotation of an irregularly shaped nucleus or a surface with heterogeneous composition. These variations typically manifest as amplitude changes of only a few percent, necessitating precise measurements collected over extended durations. The rotation period significantly influences the distribution of solar heating across the nuclear surface, impacting outgassing patterns and potentially generating observable asymmetries within the coma or tail structure. Understanding these rotational effects is fundamental to the proper interpretation of morphological observations. Rapid rotation can induce centrifugal stresses that exceed the mechanical strength of loosely bound cometary material, potentially leading to mass shedding or catastrophic structural failure. Conversely, slow rotation might suggest either a high-density nucleus or considerable internal cohesion. Non-principal axis rotation, a common phenomenon among smaller solar system bodies, creates complex photometric signatures requiring sophisticated analytical techniques to extract meaningful physical parameters. Such rotational states may be consequences of past fragmentation events or asymmetrical outgassing processes. Successful determination of Atlas's rotation period would represent the first such measurement for an interstellar object, enabling comparisons with the rotational properties of solar system comets. This comparison would test the hypothesis that formation within different stellar environments produces objects with distinct rotational characteristics. The assessment of contamination poses another significant challenge. Atlas's transit through our solar system raises important questions regarding the exchange of contaminants between interstellar objects and the objects within our local environment. A comprehensive understanding of these processes has broad implications for astrobiology and the chemical evolution of planetary systems. Solar wind particles, carrying isotopic signatures characteristic of our Sun, may become embedded within Atlas's surface or coma. This contamination could complicate future chemical analyses. The efficiency of this contamination process depends on the interaction cross-sections and resonance times involved. interplanetary dust grains originating from within our solar system may collide with Atlas during its passage, embedding foreign material that could alter its surface composition and potentially influence subsequent outgassing behavior. This contamination could lead to misleading chemical signatures. Conversely, Atlas sheds material into interplanetary space, some of which may eventually be incorporated into solar system bodies or collected by future sample return missions. This material carries chemical signatures from other stellar systems, representing a form of natural cross-contamination between star systems. Atmospheric escape from Earth and other planets contributes trace amounts of planetary material to interplanetary space, a small portion of which may be collected by passing interstellar objects. Although extremely dilute, this contamination provides a mechanism for transferring planetary signatures across interstellar distances. Understanding these contamination processes is crucial for assessing the pristine nature of interstellar objects and for guiding the interpretation of chemical analyses that might detect unexpected signatures resulting from contamination rather than intrinsique composition. The design of future missions dedicated to studying interstellar objects necessitates innovative spacecraft designs and mission architectures capable of accommodating the rapid response timelines and extreme velocity requirements imposed by these fleeting visitors to our solar system. Rapid launch capabilities necessitate either pre-positioned spacecraft or advanced propulsion systems capable of achieving the velocity changes needed to intercept these fast-moving objects. Conventional chemical propulsion proves insufficient for most intercept scenarios, demanding unrealistic propellant requirements. Solar sail technology offers potential advantages, providing continuous acceleration without propellant consumption and enabling trajectory modifications post-launch. However, solar sails require large surface areas and sophisticated attitude control systems. Nuclear propulsion concepts currently under development could provide the high specific impulse necessary for ambitious interstellar object missions, including potential sample return capabilities. Such capabilities would revolutionize our understanding of these cosmic visitors. However, these systems require substantial technological development and rigorous testing. Mission designs must accommodate the limited warning time typically available upon the detection of an interstellar object. This necessitates pre-approved mission concepts, standby spacecraft, and streamlined decision-making processes that can be rapidly activated when suitable targets are identified. The scientific return from dedicated interstellar object missions would significantly surpass that achievable from remote observations alone, providing detailed compositional analyses, internal structure determinations, and potentially returning samples from other stellar systems to Earth-based laboratories for analysis. The development and maintenance of a comprehensive database is paramount. Each interstellar object detection contributes valuable data to a growing database that will eventually facilitate statistical studies of these cosmic wanderers and their relationship to galactic structure and stellar evolution. Standardized data formats and analysis procedures are essential to ensure that observations from diverse facilities and time periods can be effectively combined for comparative studies and population analyses. Such standardization requires close coordination among international astronomical organizations. The accumulating database will eventually reveal correlations between object characteristics and trajectory properties, potentially indicating common formation mechanisms or evolutionary processes operating throughout our galactic neighborhood. Machine learning algorithms, trained on large data sets, may identify subtle patterns and relationships that escape traditional statistical analyses, potentially revealing new categories of interstellar objects or unexpected correlations between observable properties. Long-term database maintenance requires careful curation and quality control to ensure that data remain accessible and useful for future researchers, even those employing analysis techniques not yet conceived. Archival standards must anticipate technological evolution and changing research needs. The database will serve as an invaluable resource for planning future observations and missions, enabling researchers to identify knowledge gaps and prioritize investigations that maximize scientific return from limited observational opportunities. The unusual characteristics of ATLAS are stimulating significant advances in the theoretical understanding of cometary physics, dust dynamics, and thermal processes. These advances will benefit studies of both interstellar and solar system objects. Advanced computational models, incorporating complex chemistry, multi-phase physics, and three-dimensional structures, are being developed to explain the full range of observed phenomena. These models require sophisticated numerical techniques and substantial computational resources. New theoretical frameworks for understanding particle acceleration and transport in cometary environments are emerging to explain the unusual morphological features observed in ATLAS. These frameworks may find applications in other astronomical contexts involving dust and gas interactions. Improved models of thermal processes in heterogeneous porous materials are being developed. To understand how solar heating affects objects with different formation histories and structural characteristics compared to typical solar system bodies. The integration of observational constraints with theoretical predictions creates valuable feedback loops that refine our understanding of fundamental physical processes while simultaneously revealing areas where current models remain incomplete or inaccurate. These theoretical advances will enhance our ability to interpret observations of future interstellar objects and may reveal universal principles applicable to small-body physics throughout the galaxy. The discovery of ATLAS underscores the transformative impact of modern survey capabilities on our ability to detect and study interstellar objects, pointing towards even more dramatic improvements expected from next-generation facilities. Current surveys are limited in their detection rates by factors such as telescope aperture, detector sensitivity, and data processing capabilities. Upcoming facilities will improve all these aspects, dramatically increasing the discovery rate for interstellar objects. The Vera Rubin Observatory, slated to begin operations soon, will survey the entire visible sky every few nights with unprecedented sensitivity, potentially detecting dozens of interstellar objects annually once fully operational. Advanced data processing algorithms, incorporating machine learning and artificial intelligence, will enable real-time identification of moving objects and rapid classification of their orbital characteristics, accelerating the time between detection and follow-up observations. Space-based survey systems currently under development will provide continuous monitoring capabilities, unaffected by weather, atmospheric turbulence, or daylight constraints that limit ground-based observations. Such systems could detect interstellar objects at significantly greater distances. The evolution from detecting a few interstellar objects per decade to potentially dozens per year will fundamentally transform our understanding of these cosmic visitors, shifting from studies of individual oddities to statistical analyses of representative populations. The study of ATLAS exemplifies the critical role of international cooperation in maximizing the scientific return from brief observational opportunities in modern astronomy. Coordinated efforts spanning multiple continents and organizations are essential for comprehensive investigations. Time zone differences enable continuous monitoring as objects move across the sky, with observations being handed off between facilities as Earth's rotation brings different telescopes into favorable positions for observation. This coordination requires meticulous planning and robust communication systems. Resource sharing allows access to specialized instruments and techniques that no single institution could independently maintain. International partnerships enable investigations that would be impossible for any individual organization to undertake. Standardized protocols for data sharing and analysis facilitate rapid collaboration between research groups worldwide, enabling comprehensive studies that incorporate diverse observational perspectives and analytical techniques. The success of International cooperation in studying ATLAS establishes valuable templates for investigating future interstellar objects and demonstrates the benefits of coordinated astronomical research in addressing complex scientific questions. Future interstellar object investigations will benefit significantly from the collaborative frameworks established during ATLAS observations, enabling more efficient use of global astronomical resources and maximizing scientific return from these rare cosmic encounters. The discovery and investigation of ATLAS presents exceptional opportunities for public education and outreach, connecting current research with fundamental questions about our place in the universe and the nature of cosmic evolution. The interstellar origin of ATLAS captures the public imagination in a way that typical astronomical discoveries rarely achieve, providing natural entry points for discussions of stellar evolution, galactic structure, and the processes that shape our cosmic environment. Real-time observations enable educational programs that follow scientific investigations as they unfold, demonstrating how astronomical research actually proceeds and highlighting both the excitement and challenges inherent in frontier science. The interdisciplinary nature of ATLAS studies showcases how modern astronomy integrates physics, chemistry, geology, and computer science to address complex scientific questions requiring diverse expertise and analytical approaches. Educational materials developed for ATLAS outreach will serve as valuable resources for future interstellar object discoveries, building public understanding of these cosmic visitors and their scientific significance for understanding galactic evolution. The global nature of ATLAS observations demonstrates how international scientific cooperation addresses questions that transcend national boundaries and require collaborative approaches that reflect the universal nature of scientific inquiry. The investigation of ATLAS represents merely the beginning of a new era in interstellar object studies, an era that will dramatically expand our understanding of galactic structure, stellar evolution, and the diversity of planetary formation processes throughout our cosmic neighborhood. Improved detection capabilities will reveal whether ATLAS represents a typical example of interstellar visitors or an unusual specimen that happened to capture our attention. The true diversity of these objects remains largely unknown. Dedicated missions to study interstellar objects in detail will provide a comprehensive understanding that complements, but far exceeds, the information available from remote observations alone. Such missions may reveal entirely unexpected characteristics invisible to Earth-based studies. The accumulating database of interstellar object properties will enable statistical studies that reveal patterns and correlations invisible in small samples, potentially identifying formation mechanisms and evolutionary processes that operate throughout our galaxy. Long-term monitoring of interstellar object detection rates and characteristics will provide insights into galactic evolution, stellar system formation efficiency, and the processes that regulate material exchange between different regions of our cosmic neighborhood. The techniques developed for studying ATLAS will benefit investigations of solar system objects, enabling more detailed characterization of comets, asteroids, and other small bodies that preserve information about our own planetary system's formation and evolution. At the molecular level, ATLAS exhibits quantum mechanical processes that govern how absorbed solar energy drives chemical reactions and phase transitions within its nucleus. Understanding these fundamental mechanisms requires sophisticated theoretical frameworks that bridge quantum chemistry and macroscopic thermodynamics. Photodissociation of molecular species in the coma occurs when ultraviolet photons possess sufficient energy to break chemical bonds, creating reactive fragments that may recombine into new compounds or escape into space. These quantum processes determine which molecules survive long enough for spectroscopic detection. Electronic excitation states in various molecular species produce the characteristic emission lines observed in ATLAS's spectrum. Each transition corresponds to specific quantum energy levels that depend on molecular structure. and environmental conditions within the coma. Vibrational and rotational quantum states of molecules provide additional spectroscopic signatures that reveal temperature, density, and chemical composition within different regions of the expanding coma. These quantum signatures enable remote determination of physical conditions impossible to measure directly. Quantum tunneling effects in chemical reactions become significant at the low temperatures characteristic of cometary nuclei, potentially enabling chemical processes that would be forbidden under classical thermodynamics. Such effects may contribute to the unusual chemistry observed in Atlas. The quantum mechanical nature of photon interactions with matter determines absorption and emission efficiencies that control how solar radiation heats the nucleus and drives outgassing processes. Understanding these interactions requires detailed quantum calculations for complex molecular systems. The expansion of gas and dust from Atlas's nucleus creates complex hydrodynamic flows that determine coma structure, particle transport, and observable morphological features. These processes require sophisticated fluid dynamics modeling that accounts for multi-component flows and varying thermodynamic conditions. Gas expansion from discrete source regions on the nuclear surface creates jets and collimated outflows that interact with the ambient coma environment through shock formation, turbulent mixing, and momentum transfer processes. These interactions shape the overall coma structure and particle distributions. Dust grain entrainment in expanding gas flows depends on particle size, gas density, and local velocity gradients that vary throughout the coma. Small particles couple efficiently to gas motion, while larger grains follow more independent trajectories determined by gravitational and radiation pressure forces. Non-equilibrium thermodynamics characterize conditions within the expanding coma where different molecular species may have distinct temperatures and velocity distributions that evolve as the gas expands and cools. These conditions affect chemical reaction rates and spectroscopic signatures. Computational fluid dynamics simulations incorporate realistic nucleus geometry, heterogeneous outgassing sources, and multi-species chemistry to predict observable coma characteristics. These calculations require substantial computational resources and sophisticated numerical methods to capture relevant physical processes. The unusual morphological features observed in Atlas, particularly the sunward extension of scattered light, challenge existing hydrodynamic models and may require new theoretical frameworks that incorporate exotic physics or unusual boundary conditions. Atlas's passage through the heliosphere exposes it to complex magnetic field environments that influence charged particle motion, plasma chemistry, and electromagnetic signatures, detectable by sensitive instruments. These interactions provide additional diagnostic tools for understanding the comet's behavior. The interplanetary magnetic field embedded in the solar wind creates preferred directions for charged particle motion that may contribute to asymmetric coma structures or directional outflow patterns. Such effects depend on the local magnetic field orientation and strength at the comet's position. Photoionization of neutral species in the coma creates charged particles that respond to electromagnetic forces differently than their neutral counterparts. These ions follow complex trajectories determined by the balance between gravitational, electric, and magnetic forces. Magnetic reconnection events in the solar wind environment may create localized acceleration regions that affect charged particles near Atlas, potentially contributing to unusual particle signatures or electromagnetic emissions detectable by radio telescopes. Plasma instabilities driven by the interaction between the solar wind and Atlas's ionosphere may generate electromagnetic waves detectable at radio frequencies. Such emissions would provide information about plasma conditions and magnetic field structures near the comet. Advanced magnetohydrodynamic simulations model the complex interactions between Atlas's expanding coma and a magnetized solar wind environment to predict observable electromagnetic signatures and understand the underlying physics of these interactions. Future high-resolution spectroscopic observations may eventually determine isotopic ratios in ATLAS, providing direct information about nuclear processes in its parent star system and constraining models of stellar nucleosynthesis and galactic chemical evolution. Carbon isotope ratios reflect the balance between different nuclear burning processes in the parent star, with carbon-12 to carbon-13 ratios serving as indicators of stellar mass, evolutionary stage, and metallicity. These measurements require extremely high spectral resolution and signal-to-noise ratios. Oxygen isotope signatures provide information about stellar nucleosynthesis pathways and potential contamination from supernovae in the stellar environment where ATLAS formed. Different isotopic ratios indicate formation around stars with varying masses and evolutionary histories. Nitrogen isotope measurements constrain models of stellar evolution and galactic chemical evolution by revealing the efficiency of nitrogen production in different stellar environments. These signatures preserve information about conditions billions of years ago when ATLAS formed. Deuterium to hydrogen ratios provide insights into primordial nucleosynthesis and subsequent chemical processing in interstellar space and stellar environments. Such measurements challenge current observational capabilities, but would provide unique constraints on cosmological and galactic evolution models. The technical challenges of isotopic measurements from such distant, faint objects require next-generation instruments with unprecedented sensitivity and spectral resolution. Future space-based observatories may eventually achieve the capabilities needed for detailed isotopic analysis. The complex chemistry occurring within ATLAS's coma involves hundreds of potential reactions between various molecular species, ions, and radicals created by solar radiation and electron impact processes. Understanding this chemistry requires sophisticated network models that track all relevant species and reactions. Gas phase chemistry in the coma environment operates under conditions far from thermodynamic equilibrium, with reaction rates controlled by radiation fields, temperature gradients, and density variations that change continuously as the coma expands and evolves. Photochemical models incorporate detailed cross-sections for photodissociation, photoionization, and electronic excitation processes that determine how solar ultraviolet radiation drives chemical reactions and creates observable emission signatures. Electron impact chemistry becomes important in regions where photoionization creates significant electron populations that can drive additional chemical reactions through collisional processes. These reactions may produce species not formed through photochemical pathways alone. Surface chemistry on dust grains provides additional reaction pathways that may be particularly important for forming complex organic molecules through heterogeneous catalysis. Such processes could create chemical signatures that differ from pure gas phase chemistry. Chemical network calculations predict the abundances of hundreds of molecular species and their evolution with time and position within the coma. These models enable interpretation of spectroscopic observations and guide the search for new molecular signatures. The unusual characteristics of ATLAS constrain theoretical models of its formation environment and evolutionary history, providing insights into planetary system formation processes around different types of stars throughout galactic history. Formation around a metal-poor star in a galactic thick disk could explain the unusual chemical composition with different stellar nucleosynthesis products creating distinctive ice compositions not found in our solar system's formation environment. Alternative formation scenarios involve capture of interstellar material during passage through dense molecular clouds, potentially explaining unusual isotopic signatures or chemical compositions that reflect interstellar rather than stellar system processing. Collisional fragmentation of larger bodies within the parent planetary system could produce objects with unusual structural characteristics or chemical distributions that influence subsequent outgassing behavior. And observational signatures. Late-stage thermal processing in the parent system might have modified the original composition through sublimation and reaction processes that created the layered structure suggested by Atlas's complex activity patterns. Tidal disruption during ejection from the parent system could have created internal fractures or structural modifications that affect thermal conduction and outgassing efficiency in ways that distinguish interstellar objects from solar system comets. Each formation scenario predicts different observable characteristics that can be tested through continued observations and theoretical modeling, potentially enabling determination of Atlas's true origin and evolutionary history. Atlas represents a direct sample of material from distant regions of our galaxy, potentially preserving chemical signatures from stellar environments that no longer exist or have evolved significantly since the comet's formation billions of years ago. The thick disk origin suggested by Atlas's trajectory indicates formation around ancient stars that existed when our galaxy had a different chemical composition and structure than today. Such objects provide unique windows into galactic evolution over cosmic timescales. Chemical signatures preserved in Atlas may reveal information about stellar nucleosynthesis processes in early galactic history when metallicity was lower and stellar populations differed significantly from those present in our current galactic neighborhood. Comparison between multiple interstellar objects from different galactic regions and evolutionary epochs will eventually enable mapping of chemical evolution throughout our galaxy's history, providing observational tests of theoretical models of galactic formation and evolution. The preservation of ancient chemical signatures depends on the thermal and radiation environment experienced during Atlas's interstellar journey, with cosmic ray bombardment and occasional stellar encounters potentially modifying surface composition over millions of years. Future studies of Atlas and similar objects will contribute to the emerging field of galactic archaeology, using small bodies as fossils that preserve information about cosmic chemical evolution over billions of years. While Atlas shows no obvious signs of biological activity, its study provides insights into the distribution of organic chemistry throughout our galaxy and the potential for life-bearing materials to travel between stellar systems. The detection of organic compounds in Atlas would demonstrate that carbon chemistry capable of supporting biological processes occurs in other stellar systems, potentially indicating a widespread distribution of life's chemical precursors throughout our galaxy. Interstellar panspermia scenarios suggest that life-bearing materials could travel between star systems via objects like Atlas, though the extreme conditions of interstellar space make the survival of complex biological systems highly unlikely over million-year timescales. The chemical diversity observed in Atlas and other interstellar objects indicates that planetary systems throughout our galaxy may have access to chemical inventories significantly different from those available during Earth formation, potentially leading to exotic biochemistries. Contamination studies reveal how materials exchange between stellar systems through interstellar visitors, creating natural experiments and chemical transport that may influence the development of life in recipient planetary systems. Future interstellar object missions with enhanced biological detection capabilities may search for organic signatures or even preserve biological materials that could revolutionize our understanding of life's distribution throughout the cosmos. The extensive observational campaign devoted to Atlas has established new paradigms for studying transient astronomical phenomena and created datasets that will support research for decades to come. Archive development ensures that Atlas observations remain accessible to future researchers using analysis techniques not yet developed, maximizing the long-term scientific return from this unique opportunity to study an interstellar visitor. Methodological advances developed for Atlas observations will benefit studies of future interstellar objects, solar system comets, and other astronomical phenomena that require rapid response capabilities and coordinated multi-facility campaigns. The integration of professional and amateur observations demonstrates the value of citizen science networks for monitoring rapidly evolving phenomena and highlights the importance of maintaining diverse observational capabilities. Data analysis techniques pioneered for ATLAS will find applications in other areas of astronomy where similar challenges arise in studying faint, rapidly moving objects with complex temporal evolution. The collaborative frameworks established during ATLAS observations provide templates for future international astronomical projects that require coordination between diverse institutions and rapid sharing has driven innovations in observational techniques, data analysis methods, and theoretical modeling approaches that advance the broader capabilities of astronomical research. Advanced image processing algorithms developed to extract weak signals from ATLAS observations will benefit studies of other faint astronomical objects where traditional techniques prove inadequate. Machine learning applications for automated detection and classification of moving objects have been refined through ATLAS observations, improving our ability to identify and characterize future interstellar visitors. Spectroscopic techniques optimized for rapid cadence observations of faint objects enable new approaches to studying variable astronomical phenomena across diverse fields of astronomy. Computational modeling advances driven by the need to understand ATLAS's unusual characteristics will improve theoretical frameworks for studying cometary physics, dust dynamics, and thermal processes in small bodies. The integration of ground-based and space-based observations has been optimized through ATLAS studies, creating more efficient approaches to coordinated astronomical campaigns. ATLAS has captured public imagination in unprecedented ways, creating opportunities for science communication and education that connect current research with fundamental questions about our cosmic environment. Social media engagement demonstrates both the potential and challenges of communicating complex scientific discoveries to diverse audiences, highlighting the need for accurate information sources and clear explanations of uncertainties and limitations. Educational programs developed around ATLAS observations provide real-time examples of how scientific research proceeds. The study of the interstellar object ATLAS continues to reveal both the thrill of discovery and the meticulous methodology needed for dependable results. The international collaboration in ATLAS research highlights how modern astronomy transcends national borders, demonstrating humanity's unified endeavor to comprehend our place within the cosmos. Public interest in ATLAS could significantly influence funding priorities and mission planning for future interstellar object investigations, underscoring the importance of fostering continuous public engagement with astronomical research. The multidisciplinary nature of ATLAS studies showcases how modern astronomy effectively integrates various scientific disciplines and analytical approaches to address complex issues demanding extensive expertise. Future discoveries promise to build upon this foundation. ATLAS marks the commencement of a new era in interstellar object research, poised to dramatically expand our understanding of galactic structure, stellar evolution, and planetary system formation within our cosmic neighborhood. Next-generation survey systems are anticipated to detect dozens of interstellar objects annually, creating unprecedented opportunities for robust statistical studies, unveiling population characteristics and formation mechanisms currently obscured by limited sample sizes. Dedicated spacecraft missions, designed to intercept and directly study these interstellar objects, will provide a wealth of detailed information currently inaccessible through remote observation, potentially revealing unexpected characteristics and challenging established theoretical frameworks. The burgeoning database of interstellar object properties will enable comprehensive comparative studies, identifying patterns and correlations across diverse galactic environments and throughout different evolutionary epochs. Sophisticated analytical techniques will extract increasingly nuanced information from both existing and future observations, revealing subtle signatures of formation conditions and evolutionary processes. The study of interstellar objects will transition from characterizing individual anomalies to conducting comprehensive surveys, meticulously mapping the diverse outcomes of planetary formation across our galaxy. This represents a scientific revolution. The discovery and study of interstellar objects like Atlas signify a paradigm shift in astronomy, providing, for the first time in human history, direct access to materials originating from other stellar systems. This revolution mirrors other groundbreaking advancements in astronomy that have significantly broadened our cosmic perspective. From the realization that stars are distant suns to the discovery of exoplanets orbiting other stars, the capability to directly analyze materials from other stellar systems fundamentally challenges existing theoretical models and provides previously unattainable observational tests. This has the potential to revolutionize our understanding of planetary formation and stellar evolution. Future enhancements in interstellar object detection and characterization will accelerate this revolutionary progress, providing increasingly detailed insights into cosmic environments across our galactic neighborhood. The implications extend far beyond astronomy, encompassing fields such as planetary science, astrobiology, and cosmology, fostering interdisciplinary research opportunities to address fundamental questions concerning cosmic evolution. This ongoing scientific revolution will continue expanding human knowledge and perspective, providing direct links to cosmic environments billions of years old and trillions of kilometers distant. Atlas embodies the profound interconnectedness of cosmic systems, illustrating the intricate flow of materials and information between stellar systems across vast distances and timescales that dwarf human experience. The understanding that we inhabit a dynamic galactic ecosystem, where objects regularly traverse between star systems, fundamentally reshapes our perspective on Earth's place within the cosmos and the nature of our cosmic environment. These interstellar visitors serve as messengers from distant worlds, preserving crucial information about stellar environments and planetary formation processes that occurred when our galaxy was young and significantly different from its present state. Atlas's brief transit through our solar system represents a fleeting connection across immense cosmic distances, directly linking our planetary system to ancient stellar environments through a tangible material exchange. Understanding these cosmic connections provides a profound perspective on the vast scales of space and time defining our universe, while simultaneously highlighting the remarkable capabilities of human science to decipher messages emanating from the cosmic depths. The ongoing study of interstellar objects will continue expanding our cosmic perspective, unveiling the complex relationships between stellar systems and the broader galactic environment we inhabit. The questions that lie ahead are numerous. While Atlas has yielded remarkable insights into interstellar objects and galactic evolution, it has also raised profound questions that will drive astronomical research for decades to come. The mechanisms underlying the unusual characteristics observed in Atlas remain poorly understood, necessitating the development of new theoretical frameworks and advanced observational capabilities to achieve resolution. These mysteries highlight significant gaps in our current understanding of cometary physics and interstellar processes. The true diversity of interstellar objects remains largely unknown, with each new detection potentially unveiling characteristics that challenge existing theories and demand innovative explanations. Future surveys will be critical in determining whether Atlas represents a typical interstellar object or an anomalous specimen. The frequency and characteristics of interstellar visitors offer valuable insights into galactic structure and evolution, complementing other astronomical observations. However, the interpretation of this data requires a sophisticated understanding of complex dynamical and evolutionary processes. The intriguing possibility of detecting artificial objects among interstellar visitors raises profound questions about the prevalence of technological civilizations and our capacity to identify evidence of extraterrestrial intelligence within astronomical observations. These compelling questions will stimulate continued research and technological development, driving advancements in observational capabilities and theoretical understanding that will broadly benefit the field of astronomy. In closing, our journey through the recent discoveries surrounding Atlas, the so-called second comet, has demonstrated how a single cosmic visitor can fundamentally transform our comprehension of the universe. Regardless of whether you're preparing for sleep as dawn breaks in Tokyo, finding solace in these words during London's evening quiet, or discovering this exploration during an afternoon break in Sao Paulo, you've been a participant in something truly remarkable. The observed green transformation of Atlas during September's lunar eclipse symbolizes more than just a color change. It embodies the dynamic nature of our cosmic environment, where ancient materials from distant star systems continuously evolve and reveal their secrets as they encounter new environments. The unexpected rapid brightening, the mysterious sunward glow defying conventional physics, and the exponential increase in cyanide production all indicate processes we are only beginning to comprehend. The confusion surrounding the so-called second massive comet highlights how rapidly information can spread and be misinterpreted in our interconnected world. While Comet Bernoulli-Bernstein is indeed exceptionally large and approaching our inner solar system, its arrival is still years away, and it poses no threat. The viral narratives conflating multiple objects underscore the critical importance of meticulous, patient scientific investigation in our age of instantaneous information dissemination. As Atlas hurtles towards its perihelion on October 30th, hidden from our earthbound perspective behind the sun's glare, spacecraft dispersed throughout our solar system will witness its most dramatic moments. These robotic observers will acquire data impossible to obtain from Earth, contributing crucial pieces to the puzzle of this cosmic messenger's true nature. What resonates most profoundly about Atlas is its embodiment of the interconnectedness of our galaxy. This ancient wanderer carries chemical signatures from stellar environments that existed when our cosmos was young, journeying for millions, or perhaps billions, of years through the void between stars before briefly illuminating our corner of space. In studying Atlas, we engage in a form of galactic archaeology, deciphering messages inscribed in ice and rock by distant suns. Tonight, as you prepare for rest, consider that telescopes above our atmosphere are diligently tracking this alien visitor as it races towards its rendezvous with our sun. In the coming weeks, as Atlas emerges from solar conjunction and embarks on its long journey back to interstellar space, it will carry traces of our solar system's signature, potentially seeding distant regions of our galaxy with particles that once danced within Earth's magnetosphere. The questions raised by Atlas will far outlast its fleeting passage through our cosmic neighborhood. Each unusual characteristic challenges our understanding and pushes the boundaries of theoretical physics. As we eagerly await the next interstellar visitor, we can confidently expect that it, too, will surprise us, revealing new facets of the cosmic environment we are only beginning to explore. Until our next encounter under these night skies, keep looking up, keep questioning, and remember that you are part of a universe far stranger and more wondrous than we ever dared to imagine. Sweet dreams, fellow cosmic travelers. If tonight's exploration has ignited your curiosity about the ongoing mysteries of Atlas, I encourage you to share your thoughts in the comments below. Which aspect of this interstellar visitor intrigues you most? Are you planning to observe the comet's emergence from solar conjunction in November? Your participation helps cultivate a community of midnight science enthusiasts who find wonder in the cosmos. Don't forget to subscribe for further in-depth explorations of the universe's most captivating mysteries. And remember to ring that notification bell so you'll be among the first to learn about new discoveries emerging from the cosmic depths. The universe is vast, brimming with secrets awaiting discovery, and together, we'll continue exploring them, one gentle night at a time. What happened to Comet Atlas on September 7th, during the lunar eclipse, is rewriting everything we thought we knew about this mysterious interstellar visitor. Just a month earlier, astronomers confirmed Atlas was producing virtually no diatomic carbon. Yet, almost without warning, it erupted into a dazzling green fluorescence, displaying molecules that prior spectroscopic studies claimed were absent. And this was only the beginning, a chain of discoveries that could upend the established physics of comets. As the world watched Atlas draw closer to perihelion, the Hubble Space Telescope captured something unprecedented, a sunward extension of scattered light, 10 times longer than the comet itself, stretching directly toward the sun. This defied the conventional rules of radiation pressure and shook astronomers' confidence in long-standing models. Meanwhile, viral claims of a massive second comet hurtling toward Earth only fueled confusion. In truth, that object was Comet Bernoulli-Bernstein, whose distant, slow approach had been mistakenly conflated with Atlas's spectacular and unusual activity. Before we dive deeper into this cosmic mystery, I invite you to like this video, subscribe to the channel, and drop a comment below telling me where in the world you're watching from. It's always incredible to see how people across the globe connect through these stories of discovery, from stargazers under quiet night skies